Have you ever looked at a complex, curvy object like a vase and wondered, how could we possibly find its exact volume? Well, it turns out that with a little bit of spin and the power of calculus, we can take a simple 2D function, turn it into a 3D solid, and measure it perfectly. Let's dive in and see how it's done. So here's our game plan for this explainer. We're going to start from the ground up, first seeing how to spin simple curves into solids. Then, we'll get our hands on the basic disk method. After that, we'll mix it up by carving out a hole using the washer method. We'll even look at some more advanced rotations, and finally, we'll wrap it all up with a complete volume toolkit.
All right, section 1, spinning curves into solids. This is the big idea, right? We're taking something flat, like a line on a piece of paper, and imagining it spinning through space to create a real three-dimensional object.
Okay, let's kick things off with a real question. How would you actually go about calculating the volume of a vase? I mean, you can't just use a simple formula like length times width times height, right? Those curves make things way more complicated.
And here's the genius of it, and this is where calculus really shines. The trick is to slice that vase into an infinite number of paper-thin coins. This is the core strategy of integration. We take a really complex problem, break it down into countless simple little pieces we can solve, and then just add them all back up.
And that idea of slicing brings us to our first major tool. Section 2, the basic disk method. This is where we learn how to mathematically build and add up all of those tiny little disks. To get going, let's start with something we all know, the volume of a coin. I mean, a coin is really just a super short cylinder, right? And that formula is easy. Pi times the radius squared times the height. We're about to take this simple idea and give it a serious calculus upgrade.
Now, this right here, this is the translation that makes it all work. We're shifting from static geometry terms to dynamic calculus ones. So our radius, r, isn't a fixed number anymore. It's actually our function f of x, because it changes. And the height, h, becomes dx, which represents that infinitely tiny thickness of each coin. And when you put it all together, you get the disk method formula. Now, I know it might look a little intimidating, but don't let it fool you. That big S-looking symbol, the integral, that's just our super-powered adding machine. It's just summing up the volumes of pi times radius squared times thickness for every single one of those infinite paper-thin coins. Now, to make this totally manageable, here is a rock-solid 5-step process you can use every single time. Sketch it out, figure out your axis of rotation, find your start and end points, your limits of integration, set up the integral, and finally solve it. You follow these steps, you can tackle any disk method problem. Okay, theory is great, but let's put this process to the test. We're going to take the function y equals the square root of x, and we're going to rotate the area underneath it around the x-axis, just on the interval from x equals 0 to x equals 4. So let's break this down. Our radius, r, is just the height of the function itself, which is the square root of x. The problem tells us our limits, our boundaries, from 0 to 4. We just plug that straight into our formula. Volume equals pi times the integral from 0 to 4 of the square root of x, squared dx. And check this out, it simplifies so nicely to just pi times the integral of x. Okay, quick heads up. I've got to warn you about a very common mistake. It is so easy to forget to square the radius. Just always remember the formula comes from the area of a circle, pi r squared. That little square is absolutely essential, so always double check you've got it in there.
And after we solve that simple integral, we get our answer. The volume is 8 pi. Just like that, we found the exact volume of this curved shape. Fantastic!
Okay, now that we've mastered the disk method, let's build on it. Section 3 is all about the washer method. And this answers a really good question. What if the 3D shape we make has a hole right through the middle? Well, if you punch a hole in a disk, what do you get? A washer. And the logic is pretty much the same. But now we've got 2 radii to worry about. A big outer radius, which we'll call capital R, and a smaller inner radius, little r. So our formula is just the volume of the big outer disk minus the volume of the little inner disk. It's just pi times the integral of big R squared minus little r squared. It's really that simple. Let's try it. We're going to rotate the area that's trapped between 2 different curves, the simple line y equals x and the parabola y equals x squared. We'll spin that whole region around the x-axis. One of these will give us the outer edge, and the other will carve out the hole. So between x equals 0 and 1, the line y equals x is on top.
making it our outer radius r, and the curve y equals x squared is on the bottom, so that's our inner radius r. We set up the integral, pi times the integral from 0 to 1 of x squared minus x to the fourth dx. A little bit of calculus later, and we get our final volume, 2 pi over 15.
We've totally got the basics down now, so let's level up a bit in Section 4, Advanced Rotations. What happens when we don't just spin around the plain old x or y axis?
There are really two main variations you'll see. First, rotating around a shifted axis, say the line y equals -1. The trick is remembering that the radius is always the distance from the axis of rotation to the edge of your shape. So we just measure from top to bottom. That's our function, the square root of x, minus the axis, -1, that gives us a brand new radius of the square root of x plus 1. The second scenario is rotating around the y-axis. All we have to do here is flip our thinking. We solve our function for x, and our thin slices are now horizontal, so we integrate with respect to dy. Everything's just turned on its side, but the main idea of adding up disks is exactly the same. All right, let's pull all of this together in our final section, your volume toolkit. This is your quick and dirty summary of everything we've just covered, all in one spot. This table pretty much lays it all out. Whether you're using the disk method for a solid shape, the washer method for something with a hole, or rotating sideways around the y-axis, it all comes down to the same building blocks. You're just setting up pi times the integral of some radius squared, either with dx or dy. If you take just one thing away from this whole explainer, please let it be this. It doesn't matter how complicated the problem looks. It always comes down to the exact same core task, correctly identifying the radius or radii and figuring out the direction of your slice. You get that right? The rest is just plugging and chugging. So there you have it. You now have the fundamental tools to find the volume of pretty much any shape made by rotation. So think about the world around you. What's the first real-world object? A coffee mug, a bowling pin, maybe a lampshade that you would want to measure first?